Are we on? Hey, hey, how's it going, guys? How we all doing today? So, why are we here? Uh, well, I was working on my game recently, and I actually found a good application for something called linear equations, or making your own linear equation. And I'll get into all that technical mumbo jumbo in a little bit, but I wanted to start out with I was never really like great with math. Like I've taken a lot of like calculus and other high level math stuff in college, like linear algebra and stuff like that. But I never considered myself like super good with math. I definitely have my strengths and weaknesses. But one thing I did really like is like in math, um, you have this grid system that you see here, and you might be familiar with seeing this like just in high school math or whatever. But what's really cool about this grid is we can use it for video games, and we could use it to represent like a level or like a world in a video game. And that's something that really like caught my attention early on. So like if we're just looking at this graph, it's kind of like a coordinate system, almost like, you have streets and avenues in a city. So like if we go over here, for example, I'm just gonna make this a little bigger. But this is called, yeah, we'll just call this a grid. This is just our grid for now. But you can see we have numbers, going positive to the right, negative to the left. So 2, 4, 6, 8, and we have the same thing with the vertical axis. So the horizontal axis is typically called x, and that's where that x you're solving for is usually about is all about. And the top one here is called y, x and y. So this graph, let me kind of move it a bit. This graph is also known as an XY graph or a two-dimensional graph because you got your X dimension and your Y dimension going up here. But what does all this really do for us? So let's say like we're making a level in our. Sorry, I'm just checking to make sure that my mic is still working and I'm not on mute. So let's say like we're making a game, like just like a two-dimensional game, and we wanted to kind of make a little shape, like let's say we make a house. So how can we tell the computer like where to draw the lines or like how to draw the points? So what we can do is we can tell the computer, hey, we're going to use this XY grid, and I'm going to give you the coordinates, the x and y coordinates as we call them, and basically the points on the graph. So if we want to go, let's say, we can start our house kind of like, let's say over here. So we'll start by moving to the right, let's see, 2, 4, 6, 8. So x is 8, and we can move up, let's see, let's start here at 2 and put a point there. And now we'll do the same thing for some of the other points. We'll put maybe a point there, point there. We'll make just a little triangle shape. So we have these points now. We kind of put a triangle, as you can see with my amazingly straight lines. Oh, there we go. But what are these points, or how can we actually like provide these points to the computer? Because now we have a system where we can actually give like a position in the world, like okay, you go to the right this amount and you go up this amount, or you go to the left this amount and you go up this amount or down this amount. So what we could do is we'll give them the coordinates like we were saying. So typically when we write coordinates in math, we put it in parentheses, and our first coordinate is we start with the x, so 2, 4, 6, 8, and then we go up 1 for the y, so 2. So our first coordinate is 8, comma 2. And this would be the x value, and that's the y value. And we do the same thing for the other points too. So if you want, you could try to do this on your own, but let's see. So we'll do the next point. So we go 2, 4, 6, 8, 10. That's where this was on the x-axis. These are called axis, or axes. Axi? I don't know. This is an axis. So you have an x-axis and a y-axis. Okay, so anyway, our point here is that x is 10, and y is 2. And same thing for the other points. See if you can solve those for yourself real quick while I write them down as well. By the way, this center point here is 0, 0. This is if you're, so x is 0 and y is 0 right at that center point. So if we go 2, 4, 6, 8, 10, 12, so 12 for that x. And then what's the y value? Is 2. And now our last point, we go 2, 4, 6, 8, 10, and then up to 6. 10, 6. And this is basically how we plot points. This is called plotting points on a graph. Is how we tell the computer where a certain thing is located in the world. So like if I, you can imagine this is like a game world and maybe this triangle is like a weapon or something, or maybe not a weapon because it's a little too big for that, but like a, let's say a very small closet, a triangle-shaped closet. This is, you can describe it and tell the computer where to actually plot these points. So this became really popular, and well, not just even before computers came out, but before, way back in the day with original math that like people made in the 1600s, making these equations and all these, basically working with x, y, and z axes, and that's what you're talking about, like in 2 and 3 dimensions. So like this, for example, is a 2-dimensional graph. If we add z, that would be going, making depth in this direction, if you can kind of imagine that. So yeah, that's just a quick, I just wanted to quickly show just the basics of using a graph and what kind of the graph is. And we'll move on in a minute. Sorry, I don't have a script or anything, so this isn't your typical YouTube video. So be able to show that this is the x-axis before and y is up here, and this really came in handy for computers and being able to just even describe things in motion, using physics formulas to, solve for speed going in like the x direction, or, speed going in a combination of those directions, x and y. These graphs can, this graph system can be very useful for that sense. I kind of mentioned that. But all different types of math come from this, and sometimes we might even have data that we want to kind of plot along this graph. So one of the things that I was working on in my game was that I have a tank game that I'm making. And with the tank game, it plays a reload sound effect after you shoot a projectile. So every time you shoot a projectile, is this like reloading bar here telling you that you're reloading over time. And while that's, reloading, it's playing this reload sound effect. So I know that the reload sound effect is exactly 3 seconds. It's a really bad S. 3 seconds in real life time. So it's like boom, that sound is like about it. So in my game, it's exactly 3 seconds long. But I was thinking like later on in my game, you get like a piece of armor that makes it so you can reload a lot faster. So instead of the reload and the reload audio taking 3 seconds, it would take 1.5 seconds, which is half of 3. So it would take half the amount of time. Let's see. We have that going for us. But I also found a way that I can take that audio sound that's playing while we're reloading and actually speed it up by a factor. By basically, make it twice as fast or, 7 times as fast or 3 times slower or whatever. Basically by a multiple. So let's make a chart real quick of our data. And we'll just call this I know it's painful watching me write letters with this. Reload time. And the reload time and the sound effect are the same time, if that makes sense. So it takes 3 seconds to normally reload, and that's what you're hearing. But the problem I wanted is I might have some armor or something in the game that speeds up your reload time. So I need a way to be able to dynamically or basically give my code a reload time and tell me how fast I should speed it up by. We'll call this our multiplier. Mult speed. So, since our reload time starting at 3 seconds, our multiplying speed, that's just 1, because anything times 1 is itself, because that's just our starting point. Because we're not multiplying by anything, we're not changing the speed of the reload time. But for our next one, if the reload time is, half that time, so that means it's going to be twice as fast, right? Because the reload time, instead of taking 3 seconds, is now taking 1.5 seconds. That's twice as fast. So how much do we need to speed up our track by, or, our reload sound effect by? And that would be 2. We need to make it twice as fast. So with this information, we actually already have enough to create what's called a linear equation. A linear equation. So, what is that exactly? What the hell is a linear equation? So, in my code for my game, for example, I have a reload time. I know the reload time, and I want to get out what speed I should set the audio to. So if I put into the equation 3 seconds, I should expect to get 1. If I put in 1.5 seconds, I should expect to get 2. And if I put in any number, really, or whatever you want to put in here, you can then get an equivalent multiple speed out from it. But how do I go about doing that for any time? So there's actually a way we can do this using some math that people back in the day, figured out, and we'll get into that in a second. But if you notice, we have two pairs of data. We have reload time and multiple speed. How fast we're speeding up the sound effect. So we can actually take these and make them x and y coordinates, right? So let's try doing that. And before that, I'm just going to double check my notes real quick. So digest that for a second. I'm double checking my notes because I want to make sure yeah. So we can make these one. We can make one column the x, and one column the y. Okay. And what I decided when I was doing this was I made reload time our y axis and the multiple speed our x axis. Actually, let me. Make this the y, and I made this the x. And it actually doesn't matter which one you pick. I just decided to do it this way because the numbers came out a little nicer. I tried them both ways, and the numbers were not as nice when I swapped it. So that's really the only reason. But you could see when we have like a correlation between like two sets of numbers, we can actually like plot them on a graph. So let's go back to our graph and actually plot these. So our x is 1. That's about here. And then our reload time is 3, which that's about here. Okay. And now for the other one, we have reload time of 1.5. So let's actually... I can change this table a little bit. I don't want to make it too confusing. Let's leave it at that. Kind of small on the graph, but you can see that if we have now, then let's see, multiple speed of 2. So this is our x, right? So we'll go to 2, and the reload time is 1.5. So that's about, so 1 is there because this is 2, and 1.5 is about there. Oh, we actually have a selector here, so we have, let's see, on x is 2, and y should be 1.5, about there. Give me my, damn it. Okay. Technical difficulties. Okay. So we have those 2 points. And the more points that we could actually provide, the better our equation might come out to be. But we have enough to actually make an equation to give us, whenever we put in a reload time, we get out a multiplication speed. So let me draw this line now. So you can kind of see the line would look like that with our data so far. So if I gave you a reload time, let's say, of 6, what would the molt speed be? So if we go to 6 on the Y here, we can see the molt speed would be over here on the line. And that would basically give you a number that would be exactly similar to these. So it would be scaling the speed of the reload time, and putting it in other terms. Don't worry if some of this is too confusing too. Feel free to rewatch this video a couple of times because it took me a little while to understand and get used to, because we use X and Y a lot in physics and math, but this is what it basically comes down to, is being able to use it on a grid. And now with just these 2 points, we can actually make an equation that represents that. So I put in 3 for the Y and I'll get back 1. I put in 1.5 for the Y, I get back 2. And I can put that in my code to always, speed up that sound effect correctly with whatever reload speed you have. So if they came out with a new piece of armor that made the reload speed, 3 times as fast, so I'd be able to put that reload time, what would that be? 3 times as fast, so that would be like 1 second. So I'd be able to put in 1 second, and it would give me back a multiplication speed for that. So, excuse me 1 second. Okay. So now, getting back to the math of some of this stuff. So that's what this is. We're going to make what's called a linear equation. And it's called linear equation because it makes just a straight line, as you can see, meaning linear, and an equation being, the math formula stuff. So in high school, this is where some of that, like slope and y-intercept and all that stuff comes into play, is when you want to make an equation for the data you have here. So if I want to, I'm going to write down a couple of formulas. The formula, SpongeBob. The formula. We're going to write down a couple of formulas, and we'll go over it in a minute. But don't worry. These are kind of formulas you could kind of memorize, but I'm going to explain them in a second. So this is, let's do it in a different color. So the first one is, the basic formula for a linear equation is y equals m times x plus b. And we already know this y here is the same here, and this x here is the same here. But in math, we also sometimes, when we multiply things together, we sometimes don't draw this. So let me redraw it as you might see it. Y equals m x plus b. And that's the linear equation formula. I'll show you how to use it in a second. So let's change up some colors a bit. So we know this y up here is the same as this y, and this x is the same as this x. I'm going to keep those as the same color. Y, shitty y. Y, much better, equals, we'll put the x there. And I'm going to change the color for m and b, because we can actually, those are, m is what's called our slope, and b is called the y-intercept. You don't have to remember some of these technical terms, but it's more important that you get the math lesson out of it, or how you can use two pairs of correlating data to generate an equation to represent them. But yeah, so, and we have formulas for M and how to get B as well, and we'll get into that in a second. So let's rewrite our equation to not be so mathy for a bit. Go back to our blue real quick. So what do we actually have here? We have okay. Reload is equal to the slope, which is m for now. And that's going to be a numerical value that we figure out from our data. M, and then times, we can also put our multiplication in parentheses if we want, but no, I'll leave it. So our slope times, again, I'm just writing out times to be explicit here, but most of the time in math, especially when you get to formulas and stuff, they'll just put the two together like this. And that's how you know they multiply together. And you know they're separate. Like, you know, like it's not just mx or so. Anyway. So we have the reload time is equal to m times x, which is our multiple speed. So mult speed plus the. So that's what this is exactly the same thing we have here that this is here. I just wrote out what y and x are, so it's a little bit easier to not get into overloaded with too many symbols we got here. So we'll eventually be able to solve for both. So if we have the reload time, we can get the mult speed, and if we have the mult speed, we can get the reload time. And that's where some algebra comes into play, to switch things around, but we'll get to that a little later. So how do we actually solve for the slope? So that's where another formula comes into play. I'm going to go over here. Okay. So the next formula probably our last formula that we'll need for this is slope, aka m. Slope. Why did they choose m? I don't know. I'd have to look it up. Good question. But I just have this equation burned into my brain from just math over time. But yeah, like I said, slope m. I'll just go on slope m. So our formula for finding the slope is y2 minus y1. I'll get into what those are in a second. And then over, or that divided by x sub 2 minus x sub 1. So what the hell are these subs here? I've never seen that. So that's basically, I'm just numbering which coordinate I'm talking about. So in this case, we can have our slope for y2. So if we start, we can number these, right? 1, 2. I'm gonna make this part of the grid like that. Yeah. So now you can see y1 is. So actually, let me give you a second to see if you can plug in the numbers from here and put it into the slope equation. I'll do it in just a second. Okay, so if we want to plug in the numbers here, we have y2, which would be y2, so 1.5, minus y1, which is 3 seconds. And now the x2 and x1, so x1 is 1 second minus x2. This x is a little confusing here. X, so x2 is 2. Yes. And now you can literally just put that in the calculator and calculate what the slope is from there. And that should come out to, because 2 minus 1 is just 1, so anything, it's anything over 1 is just a whole number. So you have 1.5 minus 3, and the slope is negative 1.5. And that kind of makes sense actually, because you can kind of see like this line is kind of on a downward slope, because as the multiplication speed goes up, as you see in value, the reload time is going down. And that's some more power that comes with graphs is you can, with calculating this slope, this is how a lot of like math people and just things in general using math can detect like what a trend is going. Like, is it going straight down? Is it going up? That's what the slope is. And now obviously in real life, things don't always work on just a linear line. Sometimes you'll have equations or lines that look like that, for example. And that's when you get into calculus and all that. But you can start with just a simple linear equation, as you see, because our values are just going up at the same rate. That's what linear means. Like, it's the same rate. You don't have this like exponential curve of just going straight up like that. This would be an exponential curve. That's not linear. Linear is like a line like that or like that. That's, yeah. So that's what we just calculated as the slope for our data. And we can put that now in our linear equation. So now we have, for m equals that 1.5, negative 1.5. So let's rewrite that over here. We'll do y equals negative, well, I should switch to blue for that. Negative 1.5 times x plus our y-intercept, which is b. So we still have to figure out this b guy, how to solve for him or them. I shouldn't assume. It's plus b. So we have y equals negative 1.5 times x plus b. And one way we could actually solve for b is plugging in values for x and y, because we have the values that we expect for x and y, and then we can just do some algebra to solve for b. So if we have, let me double check my math on this, because I don't want to confuse you guys. Just triple checking my notes. Okay. So we have this over here. So let's plug in some values that we have for our reload time and multiplication speed, because since we have the slope, the y-intercept is where it's going to fall on the line, or on the x-axis. I'm sorry. The y-intercept is where our linear equation line is going to intersect with our y-axis. So basically here, that's the value we're trying to solve for. And you might be looking at this graph and be like, oh, it's 4, but we can't just say it's 4. I just drew this free-handedly, just to kind of give you an idea of what the line looks like. But you get an idea of that's what the y-intercept is. Literally, is where this linear equation line intersects with the y-axis. And remember, our y-axis in our case is our reload time. So we have, let's see, we'll go with our 3 and our 1, I believe. Yeah, that's a good idea. So we'll do, let me go back to my blue color. We'll do 3 is equal to negative 1.5 times, let's see, what is our x value for 3 is 1. So that's just times 1 plus b. And like I said, you can draw multiplication with parentheses if you want, but let's write it out. I want to make it as easy to understand as possible. So 1.5 times our x value. We do that first. Plus e, which is our y-intercept. And now we can solve these values. We will get 3 equals anything times 1 is the same, so minus 1.5 plus b. And we can just add this over, 1.5 to the other side. Add 1.5 to both sides, basically. Just doing some algebra to move it over. And now we'll get, what's 3 plus 1.5? That's 4.5. And 4.5 is b, our y-intercept. So now we have our formula. The formula. We have our final formula. So our final formula, now that we have our y-intercept and we have our slope up here, I'll do a better circle than that, Eddie. We have our slope up here, and we'll plug that into our equation. So y is equal to, let's see, negative 1.5. Actually, I'm going to stay consistent with the colors. Or try to, at least. negative 1.5, because that's our slope of the line, times x plus our y-intercept, b over here, 4.5. And that's our linear equation. So if we put in, you can check this too. If we put in, let's say for x, we put in a molt speed of 1. So this will be 1.5 times 1 plus 4.5. So that will just be negative 1.5 plus 4.5, which comes out to 3. And then y would equal 3. So that would be our reload time. And now same thing, try it for the other value too. So we put in a multiplication speed of 2 for the x. You get negative 1.5 times 2 plus 4.5. So negative 3 plus 4.5, 1.5. And that's what you get here. So you can check the equation to see if it makes sense. So now, going back to over here with reload time is equal to y, and multiplication speed is equal to x. So now you can see, using this stuff, we can, using these two formulas for slope, and then once we have enough data, we could actually solve for what the y-intercept is using some of our own data, plugging it in here. And as an exercise, instead of using the x and y values I plugged in for here to solve for the y-intercept, try using the other values instead. So instead of 1 here, try using 2, and then instead of 3, try setting it to 1.5, and it should work out the same to be 4.5 for that as well. And that's basically how you solve for the y-intercept. And then our slope formula here is the difference in y divided by the difference in x. And one way you can remember this, or I learned in high school to remember this, is you can think of y as being the martini glass standing on top of the table, so y over x, if that helps. But yeah, hold on one second. Okay, so that's good. If we have our x value, it spits out a y value for us. So if we have our molt speed, as you see, we can find out what our reload time is. But I actually ended up wanting the opposite of that. I wanted to be able to put in a reload time because I know how long my reload time is, and I want to get out what the molt speed I should use is. So we could actually do some algebra to move the y and the x around. And I'll just double check my notes to make sure I did it. I'm going to demonstrate it correctly for you guys. This algebra I even struggled with, but you could also use an algebra calculator if you're not sure on some things to double check yourself. So we have, let's make a new whiteboard real quick. Just give ourselves some space for solving this. So we have our formula that we came up with, which is y equals, put the x and the plus in ahead of time, plus mx plus b, right? That was our original formula that we had. And we know that y is equal to our reload time and our x is the multiplication or multiplier that we have to give for the speed. Mult speed or speed multiplier. That's some great that's some great drawing I'm doing right there. Mult Mult speed. Now we have okay. So now we actually have the values that we solved for this before. So we know that our equation that we want to use for our linear equation we want to use for reload time and multiplication speed, or speed multiplier, is, let's see, what were the values? M is equal to minus 1.5, and that's our slope, right? Slope. Slope is minus 1.5, negative 1.5, and our y-intercept, B. I don't know why they picked B for the y-intercept, that's a good question though. Our y int. I don't want to confuse you with that. Okay, and that's equal to 4.5. Right? Just want to check. Yeah, plus 4.5. And you can plug those in for that equation. So we'll have our final formula looking like this. So y equals minus 1 point. No, I'm going to keep the original colors. Y. Okay, so we have, like we were saying before, the reload time we get out. We have our x value in this case. So if we wanted to put in a multiplication speed for x, this equation will spit out a reload time. But for my game, I want to find out what the multiplication speed is, because I know how long the hang on, hold on. I don't want to confuse you. Because I know how long the reload time is in my game. I know the armor says, the reload time is 1.5 seconds. I know the reload time is 3 seconds. I know it's 8 seconds. So I know the reload time, but I need the equation to tell me what the multiplication speed is. So we need to, instead of solving for y, which instead of solving for reload time, we need to solve for multiplication speed. And we could do that just using some quote-unquote simple algebra. To me, no algebra is simple. But they say this is simple. So we'll start with just the addition. So we're going to subtract 4.5 from both sides to move it over. both sides of the equal sign. So then that becomes, and this cancels, so this becomes y minus 4.5 is equal to negative 1.5x. I'm gonna fix the color for that. Y and x. So as you can see, all I did was I just moved over the 4.5 for now. And now we need to bring over the minus 1.5 times x, but we just want to isolate the x on one side, and that's basically what algebra is doing, is we want to isolate one of the variables on one side or the other to be able to solve for one or the other. So we're going to divide both sides by negative 1.5. And then this cancels out. So our final equation, let's clean this up a bit, is y minus 4.5 divided by negative 1.5 equals x. So now we have the equation for, well, hold on, x should be red. Keep up with our color theme. So solving, so as you can see with algebra, we can now, if we have our y value, we can get out an x value. So if we have the reload time of 3 seconds, for example, you can do 3 minus 4.5. I think that's negative 1.5, and that divides into 1, and that divides and becomes 1. And you could check your equations too by putting that data back into the equation. But this is basically some of the. I just wanted to kind of make this video because I found like this real world application to actually using like the slope and the y-intercept stuff. Because like when I first originally learned this, like slope and like the slope formula, like the y2 minus y1 over x2 minus x1. When I was first like learning these formulas, they were just like being drilled into our heads, and we didn't really like know like the application, like where you could use this stuff. But that's some of like the cool stuff you can use some of this math for. And yeah, so like if you ever see like you have two sets of data, like an x and a y in that case, where you can like correlate the two, you can make an equation, and you can, by calculating the slope and the y-intercept, and then using this y equals mx plus b formula. And now, as you know, y and x, they represent, in our case, a reload time multiplication speed, but they can represent whatever you want for your particular problem if you're able to like plot it on a grid, for example. But yeah, so this is actually the formula I'm using in my game right now in Neural Tanks to determine what I should make what number I need to multiply to make it faster. The speed multiplier, in other words. And yeah. So thanks for tuning in. I hope this might have been useful to you. I hope it wasn't too confusing, but feel free to leave any questions you might have in the comments too. But yeah, I just wanted to kind of share like how sometimes it's really hard to learn some of this math without knowing like the actual like application to it, and I just wanted to kind of demonstrate a real life application. So yeah. Happy hunting. Have a good one, guys. Thanks again.